So welcome to the part 2 of theory questions of business stats. So without any delay, let's move to the fifth question of the series. That is, when it is appropriate to use the Poisson distribution and under what condition can the Poisson distribution be used in approximation to the binomial distribution? Explain with the help of an example. So when we can use Poisson is when the events are rare and events are independent. There is a fixed interval and the average rate should be constant. So let's see, the Poisson distribution is appropriate when you are counting the number of occurrence of an event over a fixed interval, that is time, space or area, and the following conditions are met. The very first is rare event. The event occur rarely or the probability of success is very small. And independent events, the occurrence of the event are independent to each other and the occurrence of one event does not affect the probability of other event occurring. And fixed interval, the time is being observed over a fixed period of time, area or other measure. Constant average rate, the average number of event mean occurring in the fixed interval is constant. So these are the conditions when to use Poisson distribution. Now when to use Poisson distribution as an approximation to the binomial. The very first, when the number of trials are large, the probability is small and the mean is moderate. Number of trial is large means the n should be greater than 20, probability should be less than 0.05 and the mean should be moderate. Then only we can the binomial distribution, that is B and P, can be approximated by the Poisson distribution with mean lambda is equals to n into P. So let's take an example. Suppose a factory produces 10,000 widgets a day and the probability that a widget is defective is 0.001. What is the probability that exactly 4 widgets are defective in a day? So the Poisson distribution is appropriate with lambda is equals to np equals to 10. Here the n is 10,000 and the p is 0.001. So multiplying this we get 10. Now we have to find the probability of exactly 4 defective widgets. So the probability of mass, the Poisson distribution का formula होता है P x is equals to k. Now here lambda to the power k e minus lambda divided by k factorial. Now here lambda is 10 and k, that is x, is equals to 4. Now substituting this value, so 10 to the power 4 e to the power minus 10 divided by 4 factorial. Now e is a mathematical constant. Its value is approx 2.7183. I'm not sure. You can check it. And by solving this, we get the answer 0.0189. So thus the probability of exactly 4 defective widgets is approximately 1.89%. Moving to the next question, that is, what is systematic sampling? Explain with examples what are the limitations of systematic sampling. So in systematic sampling, first we have to find the kth term. We can find k by dividing the population size by sample size. So the capital N is the population size and sample size is small n. So now let's suppose कि हमारा 1000 people का एक sample population है. Now we want a sample of 100. So k is equals to 1000 divided by 100, sample size and population size divide करके we get 10. Now 10th is the 10th term. Now we'll select every 10th term from the sample size. So let's see. Systematic sampling is a type of probability sampling method where every kth term element from a population is selected after randomly selecting a starting point. This approach is often used when population is logically or physically arranged in some order. So the step in systematic sampling is first determine the sampling intervals. So it can be calculated by n divided by small n, like this in example. Now randomly select a starting point. Randomly select a number between 1 and k, the k which we get, and this is the starting point. Now after choosing the starting point, now select every kth term element of the population. Like if we have selected 10, so now every 10th. Limitations of systematic sampling. The very first is risk of periodicity, not completely random, potential for bias and not suitable for populations with grouping. Risk of periodicity means if the population has periodic pattern that coincides with the sampling interval, systematic sampling can introduce bias. For example, if every 10th item in a production line is defective and you choose every 10th item, your sample might either overestimate or completely miss the defect rate. एंड ये कम्प्लीटली रैंडम नहीं होता है क्योंकि involves a random selection for the starting point and it is less random than simple random sampling. The method assumes the population is evenly distributed without any patterns. पोटेंशियल फॉर बायस भी होता है कि अगर कंसिडर्ड कि अगर कोई एम्प्लॉय की लिस्ट है जो कि सीनियरिटी के बेस पे ऑलरेडी अरेंज्ड है और हमने फिर इसमें से सैम्पलिंग किसी टर्म को लेना शुरू कर दिया तो इधर विल गेट ओवर रिप्रेजेंट हो जाएगा या फिर अंडर रिप्रेजेंट हो जाएगा एम्प्लॉयज का ग्रुप का. Not suitable for population with grouping. So if the population is organized in such a way that every key member share some common trait like alphabetical list या कोई भी common traits share कर रहे हैं तो systematic sampling can miss important variations within the population. So these are the limitations in systematic sampling. Moving to the next question, that is explain the sampling distribution of mean. So what is sampling distribution? Sampling distribution of mean refers to the probability distribution of sample means calculated from all possible random samples of a given size from a population. Now the key points are mean of the sampling distribution, that is mu. This means on average the sample mean will be same as the population mean. Standard error, we can calculate standard error by standard deviation divided by under root n, small n, that is sample size. Now shape the central limit theory. According to central limit theory, if the sample size is sufficiently large, typically n is greater than 30, the sampling distribution of mean will be approximately normal regardless of the population distribution. And if the population is normally distributed, the sampling distribution will also be normal for any sample size. So for large samples, the sample distribution is normal, and for small samples, it's normal only if the population is normal. So this is about the sampling distribution of mean. Moving to the next question, that is explain the expected payoff under perfect information, EPPI. How is it different from expected value of perfect information, EVPI? So let's see the theory part first and then we'll solve one question regarding this. So what is expected payoff under perfect information? So it is best possible outcome or payoff that could be achieved if we had a complete or perfect knowledge of future events or uncertainties. So in decision theory, it represents the maximum expected payoff you would receive if you know exactly which state of nature or outcome would occur before making a decision. So steps to calculate EPPI is, first you have to identify the decision alternatives, all the possible states of nature, then determine the payoff alternative under each state of nature, and for each state of nature identify the decision that yields the maximum payoff assuming the perfect information. Now calculate the payoff by multiplying the maximum payoff for each state of nature by its probability and summing the result. This is how you calculate the expected payoff under perfect information. We'll solve the question that will clear your doubts. So expected value of perfect information, this means the additional benefit or the value that would be gained by having perfect information about the future events before making a decision. In other words, it is the difference between payoff you can expect to receive with the perfect information and the payoff you would receive without perfect information. That is expected monetary value or EMV. So the formula to calculate EVPI is equals to EPPI minus EMV, whereas EPPI is the expected payoff under perfect information and EMV is the expected monetary value without perfect information. So steps to calculate EVPI is, first you have to calculate the EPPI as described earlier, and then you have to calculate EMV by choosing the decision alternative with the highest expected payoff based on the current information. Then you subtract these both to get EVPI. I know it's a bit of confusing, so let's solve the question. Suppose a company is deciding whether to launch a new product. These are the two possible states of nature, high demand or low demand. The company does not know which state will occur, but they have estimated the payoff of and probabilities for each division. Now the probability for high demand is 60% and for low demand it's 40%. And to launch a product it's 200 for high demand and low demand minus 50. Do not launch, high demand 100 and low demand 70. Now let's calculate EPPI for this. If you know the demand is high, you would choose to launch and get a payoff of 200 because among this the greatest one is 200. And if you know the demand is low, you would choose not to launch to get a payoff of 70, the biggest value. Now to calculate EVPI, what we have to do is we have to multiply the probability with this number in both and then summing up. So 0.60 multiplied by 200 plus 0.40 multiplied by 17, this gives 120 plus 28, that is 148 is our EPPI value. Now we have to calculate EMP value. So for calculating EMP value, we have to calculate the EMV value for launching a product and for not launching a product. So how you can do this? Multiply the probability with 200 plus multiply the probability of do not launch minus into minus 50, it gives 100 EVM, and the expected payoff of not launching is 100 into 60, 0.60, and 70 into 0.40, and summing it up, we get 88. The highest one is 100 EVM for payoff, expected payoff for launching, so we'll choose 100 EVM. So now for calculating EVPI, it's 148 minus 100, that gives us 48. Thus the EVPI is 48, meaning that having perfect information about demand is worth 48 to the company. So this is all about this theory part of the statics business. So all the very best for your exams. Thank you.